Our second physicist, Dr. Stockman, is here and ready to tell you. I think he's going to tell you how the universe is a hologram, possibly. I guess we'll find out.
Hi. Somebody told me there. Am I supposed to speak in here so you can hear me? Thank you. And is there a remote control for the, does this work too? Okay. So yes, I'm going to talk about the holography of the universe. And now I have to figure out which button does what. Nope. Ah, there we go. So I hope you've all seen a hologram at some point in your life. Here's one from the movies where our good friend projects a three-dimensional picture of that spaceship or whatever it is. So you can really see all three dimensions about what's going on in that picture. The trick about a hologram, though, is that all the information that you need to make that three-dimensional representation of the object there in real space all comes from a little screen that's only 2 dimensions. So all the information in that three-dimensional thing is really packed down into just 2 dimensions. That's the essence of a hologram. We think that the universe could be that way too. A couple of physicists have come up with what's called the holographic principle, saying that all the information inside any volume of space isn't really, there's not as much there as you think there is. There's only as much as you can fit on the walls. Think about this for a second. Suppose I asked you to come in and paint the walls of this room, and the ceiling up there, and the floor down there. So paint the walls, paint the whole room, right? And you would break out your calculators and your rulers. You would measure how many square meters there are in the entire auditorium. You would figure out how many square meters per gallon coverage you get on the paint. You would buy a little more probably, and you would paint everything, right? Well, first of all, don't actually do this. I think you'll get in trouble if you do that, but you get the message with this thought experiment. So it would take a lot of paint, right, to do that. Now consider doing something else. Take enough paint into this room to completely fill it up, right? That would take a lot more paint, right? We like to think that inside of a room, we can fit everything that's the whole volume of the room. What this principle says is that's not true. The only information you have in this room, the only real content in this room, is what you can fit on the walls of the room. So it's quite remarkable, and we're going to see if that's true. These ideas came by trying to meld 2 great ideas of physics that came. We call it modern physics. Now this was like over 100 years ago that they came up with this. So maybe that doesn't seem modern to you. But as opposed to classical physics, where there were 2 great theories. These were some of the first people to do it in the book called 30 Years That Shook Physics by George Gamow, who also could have been he's really one of the founders of these 2 new theories that explain how our world works. Could have been one of those real founders. He wrote this book, which is a really good read. The one principle is quantum mechanics, how things work when they're really small. Okay? And things work in a very strange way. You don't know whether it's a particle or a wave. Right? And when things are very big, that's the theory of relativity, things also work in a very strange way. And trying to understand exactly what's going on can be a bit of a difficulty. And that's one of the puzzles we've been working with, really. Since those 100 years, we haven't really figured out completely what's going on yet. First of all, when things get very, very small, I don't know if you've heard of quantum mechanics, or the fact that, well, the question is light particles. Are they particles or are they waves? The answer is, well, we don't know. Depending on what you're doing with them, they behave in different ways. Smaller things have more energy. And that's one of the weird things about quantum mechanics too. As they squeeze something to be smaller and smaller and smaller, it gets higher and higher energy. So to confine something into a small space, you have to give it more energy. And here's where we're going to try the demonstration. First, I'm going to try and turn this light on. This would have been much more impressive if that had come on. Let me see if I can debug what's going on here. Thank you very much. Now let me see if it does what I think it's supposed to do. Yeah, turn the lights down now, as low as you can without us getting in trouble. Okay. So, when I turn the juice down on this bulb, well, it gets fainter. Now it gets brighter, right? So you've all probably seen this effect. Now, if I turn it down very low, also notice that it changes color. When the filament is not very hot, right? It doesn't give off as much light, but the light it gives off is more red. When I turn it up, it's more blue. Cold, it's more red. Hot is blue. Longer wavelength light is red and is cold. Shorter wavelength light, smaller things are hotter, have more energy, and they're blue. So we have cold is red, hot is blue, cold is red, which is why sometimes we have trouble in the shower. Oh, come on, I get more of a courtesy laugh than that, don't I? Can we have the room lights, please? Fine. So if you were napping now, we want you to wake up. And now comes the other great demonstration of one of the most prevalent forces of nature. It explains why is the Earth round? Why do the planets do what they do? In fact, the evolution of the entire universe. I'm going to demonstrate this for you now. Guess what's going to happen? Okay, if that was too easy for you, how does the book know which way to go? Gravity. Yeah, but how does the gravity get there? See, there's nothing. How does it know which way to go? Anyway. Accounts for an awful lot of stuff. And the question I asked, how does it know which way to go, in fact, is a pretty deep question, and we really don't understand why. The key about gravity is that bigger things have more energy. Right? So the amount of energy I have in 1 gallon of gasoline, if I have 2 gallons of gasoline, I can go twice as far. Right? So bigger things have more energy. If I were to drop a book on your head, it would hurt. If I were to drop 2 books on your head, it would hurt twice as much. Okay, so this is explained or summarized. All physical things we know when we measure, we put on this graph. And going left and right, we have how much energy it has. And going up and down, we can plot how big is it. So there you are playing soccer, typical scale. You're sort of on the right side. And something that's bigger and heavier, for example, the Earth or even the black hole in the center of our galaxy, are bigger than we are and heavier. But there's a limit. Notice that black dot representing a black hole is on that line. The theory of relativity says you can't have anything to the right of that line or below it. You can't have something more dense than a black hole. If you get bigger to a cluster of galaxies, or indeed the whole universe, they tend to follow up along that line, but they don't cross it. That's the law of gravity that we just demonstrated here. Going the other way, you can have smaller things like a grain of sand or a pollen, right? Or something that really behaves like quantum mechanics, a single photon of light. And there we see the red ones are bigger and colder and longer. The blue ones have more energy and are a little bit smaller. Other fundamental particles like the proton and our new best friend, the Higgs boson, also lie on this same plot. And atoms too in the Higgs boson. The question we want to answer is what happens way down here? Way down there, we can't measure what's going on there. The distance to get from us to the whole universe, if I take my size, about 2 meters, multiply it by 1 billion times 1 billion times 1 billion, that gets to be the size of the whole universe. If you take now my size, our size, human size, divide by 1 billion, by 1 billion, by 1 billion, you're just barely where the Higgs boson is. You've got to go 1 billion times smaller to get down to that Planck scale. It's farther for us to go from where we are down to where those two lines cross than it is to go to the entire universe. So we're taking a journey in the sense that's 1 billion times farther than going to the edge of the universe. Of course, it's in the other direction. So, how are we going to go and measure that? You can't just go and measure something that's that small. It would be like looking for a contact lens that you dropped in your backyard by looking with Google Earth. I mean, it's the wrong scale. You can see your house maybe on Google Earth, but you're not going to find something as small as a contact lens. We use something called the uncertainty principle. Heisenberg's uncertainty principle is you can't know the position and how fast something is going exactly. This new uncertainty principle says, because of this uncertainty, you can't know exactly where something is in two directions at the same time. It's like playing checkers. The checker has to be either on this square or that square. If you're playing with your little brother or something and he puts one sort of halfway, you say, no, you can't do that. It has to be here or here. And that gives you an uncertainty, much like when you blow up a digital image of a picture you take with your camera. When you zoom in enough and see just the pixels, everything gets blurry. It's that blurriness that we're looking for. We're going to do this with an interferometer. Light goes in the side here, hits a mirror that's angled at 45 degrees, and each photon splits into two parts. They go in their respective directions, come back to the beam splitter and combine. What happens next depends on exactly how long those two arms are, or exactly where that beam splitter is. If it's off a little bit, well, so we set it up so all the light goes back. But if it's off a little bit, if the position of that beam splitter is off a little bit, some light leaks out. That's the light we're going to see to detect whether space itself is lumpy or quantized like a checkerboard. Okay, so what does it mean if we do that? Does it mean we live in a hologram? Well, no, not quite. That's being a little bit extreme. We like to think that, when I ask you, where are you? That's an easy question. Exactly where are you standing right now? But it can be a more important question to ask than just that. We like to think that space itself is emergent. Emergent means something exists on a larger scale or on a less fundamental scale. But when we look more fundamentally, exactly where is it? And this is where we get to do our own physics demonstration. First we'll look at this. Did you recognize this work of art? Maybe if I zoom out on it, it's easier to see. Right? So perhaps you've seen this at the Art Institute. When you zoom out, the image emerges from that size. So in the same way, waves can emerge from fundamental particles. And here's where we get to do a demonstration. You've all done the wave? I'd like to start over here. Do you need instructions how to do it? You can do it from a sitting position. You don't need to practice, do you? You've done this before. So we'll start over here. Okay, wake up. Start here. Go this way. Everyone shake out your arms and wake up. I know it's going to wake up. Okay, you ready? 1, 2, 3, go! Since I'm from Fermilab, we like to collide things. So if we could start one over here and one over here, watch out in the middle and see what's going to happen. You ready? 1, 2, 3, go. Very good. And there we have a pair of Higgs bosons. Thank you very much. So the question I have for you, well, first of all, when we were doing that, did the wave exist? Yeah, something existed there. I think the second one was better than the first one because you were warmed up. So you can talk about how fast did it go, how big was it? So yes, it does exist. Another question is, well, where is it right now? Well, it went away. Okay. While the wave was going on, did the wave exist in your armrest on your chair? Well, no, you look at a fundamental scale like that, things don't exist. But when we zoom back, it does exist. That's what we mean by emergent. Space-time itself could be just like that.